Okay, we are recording. So, second day of problems. I just got these posted. I was actually making up problems for today because I wasn't quite satisfied with any of the ones I'd had before. And I just got this file posted up there. So, sorry about the lateness of that. But I also finally got yesterday's, I had to re-record the video from it, and I finally got that processed this morning. So it's now available in week 6, day 3. This is week 6, day 4. So anyway, first problem, calculate the maximum deceleration of a car that is headed down a 6-degree slope. So we've tossed in a complication here. One that makes an angle of 6 degrees with the horizontal under the following road conditions. And you can assume that the weight of the car is evenly distributed on all 4 tires and the coefficient of static friction is involved. That is, the tires are not allowed to slip during the deceleration. So now for a car on dry concrete, we'll use mu sub s equals 1.0. On wet concrete, mu sub s equals 0.30. This is actually a pretty good coefficient of static friction, mu sub s equals 1.0. That would be for new tires in good condition. So that's pretty high. You can actually buy tires that have a higher coefficient of friction than 1.0. They're kind of sticky, actually, and but they're more expensive, as you might imagine. Anyway, on wet concrete, and then on ice, assuming mu sub s equals 0.100, and that's just matching the same coefficient as shoes on ice. So just a quick sketch here, a simple one. If this is a horizontal line, this road is making a 6-degree angle with the horizontal, and it just says one significant figure here. So, I would have made that a little better. So anyway, there's just a car driving down this thing and trying to stop. So that's the deal. And the car's going that way. So first thing, let's make a free body diagram for this situation. The weight of the car, mg, straight downward. That's when we would do this live and I'd ask the students what should go on the free body diagram. That's always the low-hanging fruit. And so whoever got asked first would usually say mg. And then we've got the normal force in this case, which is in that direction. And since this road makes a 6-degree angle with the vertical, this will be a 6-degree angle over here. This will be 90 minus 6. This will end up being 6 degrees again there. And then the frictional force is the other force acting in this case. And it's going to be, I didn't do a very good job drawing parallel to my road surface there. So ignore that one. Anyway, there's the frictional force. And this is static friction that we've got going on here. So since that's such a lousy diagram, I think I'm going to redraw it. mg downward. And I'll just draw a horizontal line in here. And the frictional force is parallel to the road surface. So this is our 6 degrees there. And then the normal force is perpendicular to the road surface. So it's going to be up in this direction, and this is perpendicular. The normal force there. Okay, so that's the situation. I've got a bunch of different coefficients of friction, so I'm going to solve this thing completely in variable form, and then I'll just plug in these different values for the coefficients of friction and seeing what we can get for the maximum acceleration. Now, If it's maximum acceleration, we're going to assume that the static frictional force is then maxed out. In general, the static frictional force is less than or equal to mu sub s times the normal force, but when it's maxed out, it'll be F sub s is equal to mu sub s times the normal force. So we'll have that. Now, the wrinkle that's tossed into here is that the normal force is not equal to mg because they're at angles with respect to each other. Now, we could either calculate components for both the frictional force, this is F sub s here, forgot to label it, and the normal force. But what I like to do is select a coordinate system so I only have to calculate components of one vector. Sometimes it'll be a toss-up. Sometimes you'll have two vectors for which you don't have to calculate components and two for which you do. It's a bit of a toss-up. But in this case, actually, one thing I usually let decide is the direction of the acceleration. And it's kind of a pain if you're solving for the acceleration to have it in component form. So now the acceleration doesn't belong on the free body diagram, but you can draw it maybe off to the side or something like that. The acceleration in this case is going to be going up the plane. And so it's going to fit in with a coordinate system where n and f sub s don't have to have components. So that's what I'll do. I'll let y point that way and x be up the plane like that. So this thing is tilted 6 degrees with the horizontal like the other thing, and that's my x and there's my y. So that's the coordinate system I'll use when I'm solving this thing. Okay, let's go to our usual routine here. The sum of the forces equals MA. All right, well, in this case, I've got three forces. I've got F sub s plus N plus mg is equal to MA. I hope you're getting used to thinking of this, that doesn't matter what the direction of these forces happen to be. When you're adding them as vectors, they're just added together. And so we get that. All right. Then I'll try to figure out components for each of these forces and start doing these things. Now, F sub s is just going to equal its magnitude in the x direction, or it'll equal F sub s times I hat. The normal force is just going to equal its magnitude. It's pointing in the positive y direction, so it'll be n times j hat. The acceleration is going to be back up the plane. Remember, the velocity is down the plane, but you're trying to slow this car down, so the acceleration will be opposite that. So it's also going to be in the positive I hat direction. Whoops, and its magnitude. And the only one I have to mess with is the mg. And if I look at this little diagram here, this is 6 degrees. F sub s is perpendicular to this line I just drew. So this angle would be 84 degrees, because this one plus this one will equal 90. So this is 84 degrees. And then this one here, there's a horizontal line, here's a vertical line for mg. This will be 6 degrees again. So I can draw myself a little triangle here. I've got mg. I'll figure out components in this tilted coordinate system. This is 6 degrees. And this divided by the hypotenuse of the triangle. Oh, this is a right angle down here. This divided by the hypotenuse will be the sine of 6 degrees. So this little thing down here will be mg sine of 6 degrees. And this one here, this divided by the hypotenuse is the cosine of 6 degrees. So this will be mg cosine of 6 degrees. Okay, let's do the sum of the forces in the y direction. Now, the car's going down the hill. It's going opposite the x direction that I chose. The car's not jumping off the road or sinking into the road. And so there's no action going on in the y direction on here. So the sum of the forces in the y direction equals 0. But what those forces are, I've got F sub s in the positive y direction. Oh, I never drew my components of mg. Mg will equal, let's see, minus mg sine of 6 degrees. That's in the I hat direction, and it's got a minus sign because it's pointing in the minus x direction, minus mg cosine of 6 degrees in the j hat direction. So lots of work on this thing just to get it set up. But just considering the y forces here, I'll have n in the positive y direction minus mg cosine of 6 degrees in the j hat direction. And that's it for y forces. So this is 0. So the normal force in this problem is not just the weight, it's mg cosine of 6 degrees. Now, cosine of 6 degrees is just a little bit less than 1. So it's still pretty close to the weight of the thing, but it's not equal to it. So it's less. Some of the forces in the x direction are going to equal the acceleration, which is in the x direction. Well, what do we got for forces in the x direction? All we have is the frictional force in the positive x direction minus mg sine of 6. And that will equal MA. Okay, well, we'll be solving this equation for the acceleration and then plugging in all those numbers. But let's go ahead and replace the static frictional force, which in this case is going to equal mu sub s n. But n is equal to mg cosine 6. So this will be mu sub s mg cosine of 6 degrees minus mg sine of 6 degrees is going to equal MA. And as is the case with quite a few of these problems, every one of these terms has an M in it, so the mass drops out, and I'll get that the acceleration is going to equal mu sub sg cosine of 6 degrees minus g sine of 6 degrees. Or, let's see. Now, I guess the only common factor in there is g, so I guess I could factor it out. The acceleration will equal mu sub s cosine of 6 degrees minus the sine of 6 degrees times g. All right, and that's the expression that I have to solve for here. So all it's doing is just asking me for the maximum acceleration, and this will give me that. And I can just now do 3 calculations plugging in different values of mu sub s for this. And I'll just do the 2 most extreme ones, and you can try it out for the wet concrete one. Actually, it'll be 3/10 of the result we get for the dry concrete. But if mu sub s is equal to 1, this is for part A, dry concrete, mu sub s equals 1.0, and the acceleration would be 1.0 cosine of 6 degrees. We're only going to have one sig fig on this, minus the sine of 6 degrees times 9.81 meters per second squared. So the maximum deceleration here this cosine of 6 degrees minus the sine of 6 degrees is actually 0.89, and then times 9.81. And I get pretty good at deceleration, actually. Actually, it would round to 9 meters per second squared. So that's all that works out to. For part B, actually, yeah, it's not quite the same. I'll go ahead and calculate it since we've got everything done. It'd be 0.3 cosine of 6 degrees minus the sine of 6 degrees. I wasn't right about it just being 3/10 because we still have to subtract that thing off, times 9.81 meters per second squared. Yeah, in this case, this factor in here ends up being 0.19. I'm going to multiply that by 0.81. I get 1.9, or actually 2. Oops, that was supposed to be an equal sign. A is equal to 2 meters per second squared. So actually quite a bit less than 1/3 of that. And for the scary situation, if you're coming down the hill and there's nice wet ice on there, actually wet ice might be lower than 0.100 for the coefficient of friction. In that case, you might be hydroplaning down there, which is practically zero friction. That's exciting. But anyway, we'd have the acceleration in that case is 0.100 cosine of 6 degrees minus the sine of 6 degrees times 9.81 meters per second squared. We could figure out a stopping distance, except we weren't given a speed for the car. Might be interesting to do that for this situation. See if you would even bother to stop. In the last few years, I've seen videos on YouTube of places like, the one I saw was in Colorado. There was this steep hill in this neighborhood, and people kept trying to drive up it in their giant four-wheel drive vehicles, and they'd get to a certain distance and then their wheels just start spinning and they'd go sliding back down the thing. And there was this huge bunch of dented cars because these other ones had slid down the hill into that. I saw something like that on the South Hill in Spokane a couple of years ago. Made you kind of wonder about the intelligence of people. They just kept trying to do this. uh, I get a negative number for this one. For the thing going in there, which tells me that it's not going to stop the car at all. In fact, the component of the weight down the hill by itself is greater than the frictional force. So, yeah, in that case, it's not going to be slowing down at all. It's actually going to be sliding down the hill and speeding up in this case. I better recheck that, but I'm pretty sure that's the case. 0.1 times the cosine of 6 minus the sine of 6. Yeah, I get it's tiny, but in this case, it would actually be accelerating down the hill at A equals minus 0.05 meters per second squared. So if you're coming down the hill and it has been deep road conditions, but all of a sudden you hit this slick part where it's ice, your car is not only not going to slow down, it's going to speed up as going down the hill. So there's something to watch out for. Oh, why does MG have both I hat and J hat, but not the other vectors? Actually, your mic isn't working because I've got them all turned off. So this is the best way to contact me, Cooper. Why it has it is because I chose a coordinate system where X pointed up the plane and Y pointed perpendicular to the plane. And in that coordinate system, F sub S is in the X direction, N is in the Y direction, and MG has both X and Y components. I used a tilted coordinate system. And that was to take advantage of the fact that this vector, and the acceleration would not have components in that coordinate system. Any other questions about that particular problem? It's a pretty neat one, actually, to see that especially this last situation. And I've seen situations like that. That one time on the South Hill in Spokane, people kept trying to drive up this steep street. And it was the kind of fluffy, wet snow that comes down, gets compacted, and it's really slick. And they were just, yeah, not being smart anyway. So let's try another problem. More ice here in this one. This one, I think that I've kind of modified it from a problem that was in the book, but it had nice illustrations. So a 45 kilogram block of ice on a frozen lake has a coefficient of static friction between it and the ice below of 0.10. So I think, does that match? Yeah, that matches the one that we had in this problem here. I'll flip this so we're not distracted by it. If a boy pushes on the block, as in the figure below, what minimum force will be needed to get the block to move? Well, minimum force to move something sounds like we're going to try to overcome static friction. So when that's the case, instead of having the static friction be less than or equal to mu sub s times n, we're going to max it out so it's equal to that. So F sub s will equal mu sub s times n here. Now, this is a situation where we've got a horizontal surface that it's moving on. And so let's just use an ordinary XY coordinate system here that's untilted. So X can point that way and Y can point that way. Newton's second law in vector form. I think I'll skip the sum of the forces equals ma. We know that. And actually, we're just trying to overcome static friction, so we're not so interested in the acceleration yet until we get to part C. So we'll deal with that then. But we'll have three forces, need to draw a free body diagram. I'll have mg downward. I'll have, I should have drawn that a little different. I'll have the normal force upward, and then at 25 degrees below horizontal, I'll have the force F, because he's pushing it downward and doing that. Now, ordinarily, if you've got a horizontal situation, the normal force is equal to mg, but that won't be the case here because we've got a downward component of F there. And so it makes a 25-degree angle with the horizontal. So what we can do, write Newton's second law in vector form. And in this case, we're just going to try to nudge that block so it starts to move. So we'll have N plus mg plus F is going to equal 0. Let's see, did I miss any? Oh, friction, forgot about that. Ha, these are frictional problems after all. Missed one. So there will be static friction in this case too. Rats, I was hoping it was a 3-vector problem, but it's not. Okay, well, I'll have to figure out components here. And if I look at my free body diagram there, 3 of the forces won't have components in a XY coordinate system like this, and I only have to figure out components for F. So that's kind of nice that that'll be the case. And if I redraw a little triangle just with F, so there's F, and I figure out its components in this coordinate system. This would be F sub x. This is 25 degrees. This one will be F cosine of 25 degrees, and convince yourself of that. This one will be F sine of 25 degrees. There's a right angle between those two forces. So that's what F's going to look like. So let's write all of my forces in I hat, J hat terms. Normal force points straight up. It's going to be its magnitude times J hat. Let's see, mg points straight down. So it's going to be minus mg in the J hat direction. Let's see, F sub s is going to equal its magnitude, but in the minus I hat direction. And then that force that the boy is exerting is going to be, it's got F cosine of 25 degrees in the I hat direction. Minus F sine of 25 in the J hat direction. So there, that'll be kind of nice to work with. And let's look at the sum of the forces in the I hat direction, or in the Y direction. What I would get is I've got N that's positive minus mg minus the F sine of 25. And as in the last few problems, there's no action going on in the Y direction. So those are going to equal 0. And I'm going to run out of space, but that's what this is for over here. So in this case, the normal force is actually mg plus F sine of 25 degrees. So I have it. Okay, what about the sum of the forces in the X direction? I think that's, yeah, I can still see that. Those are going to equal actually they're going to equal 0 too, because we're just trying to overcome the friction. And once we've maxed out the static friction, we'll get that thing to move. So a tiny bit bigger than this force that we figure out, and that'll nudge the block and it'll start moving. Okay, so what are they? We've got in the positive x direction, we have f cosine of 25 and minus f sub s. So f cosine 25 degrees minus f sub s is equal to 0. Or, let's see, f cosine of 25 degrees equals f sub s. Now I need to do a little bit of work here. The normal force is kind of weird. The static frictional force will equal mu sub s times n. And so I know that, but the normal force is mg plus f sine of 25 degrees. So this is going to be kind of ugly when I get it set up here, but let's just see what happens. The f cosine of 25 will equal f sub s, which is mu sub s times n, but n is that, so it'll be mu sub s times mg plus f sine 25 degrees. Yuck. And it's f that I want. So distribute that mu sub s through there, and you get mu sub s mg plus mu sub s f sine 25 equals f cosine of 25. Bring this term over to here, and I'll have f cosine of 25 degrees minus, and this is only part A, minus minus mu sub s sine of 25 degrees equals mu sub s times mg. Okay, factor the f out of each one of these things. Whoops, that one doesn't exist. And then divide by what you factor it out of. And this will be two algebra steps at once, but it will be the force necessary will equal mu sub s mg divided by cosine of 25 degrees minus mu sub s sine of 25 degrees. And yuck, what a complicated expression. It's pretty ugly, but if we just plug in our numbers here, now it turns out that a lot of the work that we did here can be used in this problem. The one thing that changes is the force F will have a plus sine of 25 on it. So that's something to look forward to on part B anyway. Won't be terrible. Okay, I forgot what mu sub s was. It's 0.1. So times the mass of the block, 45. And we're only going to be down to 1 sig fig when we're done here. No, it's 0.10 actually. So we'll have 2 sig figs on here. Okay, times 45 times 9.81 divided by that complicated mess, which I must wrap in parentheses, cosine of 25 minus mu sub s, 0.10 again, times the sine of 25. And I get a force of 49 newtons. Okay, this was a situation where the normal force was made larger because the boy was pushing down on the block partly, and that actually made that normal force larger. The normal force not only had to support the weight of the block of ice, it also had to overcome the downward component of the force he was exerting on it. In this problem, it's going to be different because he's got this rope tied around here and he's pulling it upward at the same angle. So let's see what's going to happen to our equations. Much of this is going to be repeated. We'll have the same thing there. We'll have the same N equals N along J hat, mg is going to be minus mg along J hat. Let's see, the frictional force is still going to be minus F sub s along I hat. Let's see, 1, 2, 3, and F. Here's the thing that changes. F will equal same component in the I hat direction, F cosine of 25 degrees in the I hat direction, but now it's plus F sine of 25 degrees. So this force is partially lifting the block off the ice. That's going to decrease the normal force and make it easier to move. So we should come up with a smaller force for this one than we have the first one. Okay, let's see. Some of the forces in the y direction this time. I think I can make this work. Those are going to equal 0. I'll have n plus f sine, whoops, didn't have my j hat there. F sine of 25 minus mg is equal to 0, or the normal force here is going to be mg, kicking these across, minus f sine of 25 degrees. Okay, that's the y direction. And the x direction, actually, that's going to look just like the other one, I think. Where did I write that? Yeah, some of the forces in the x direction going to equal 0. And so I'll have f cosine of 25 degrees minus f sub s again equaling 0. But things are going to be a bit different after that. Okay, so there's the normal force. F sub s again will equal mu sub s times the normal force. And that's going to be mu sub s times mg minus f sine 25 degrees. Okay, so there's the frictional force. Now, how does this compare with what I had before? F cosine of 25 will equal this thing. I need more paper. Okay, that was scratch paper. Should be able to finish it on here, I hope. Yeah, I'm bringing this equation down and I'm going to write out sub s. So F cosine of 25 degrees is going to equal F sub s, which is mu sub s times the quantity mg minus f sine of 25 degrees. And I should end up with something that's an awful lot like what I had before with one sine switch on it. So F cos 25 degrees equals, noticing we're having to be really careful with our algebra here. Okay, bring this across. So F times the cosine of 25 degrees plus mu sub s F sine of 25 degrees equals mu sub s mg. Now, how does that compare with before? Looks a lot like it, except we've got a plus sign here. And that's the difference that that thing makes. Although I'd be careful about trying to leap and just change things when I'm solving a problem like this. Anyway, if I factor out the f and then divide by everything else, I'll have f is equal to mu sub s mg divided by the cosine of 25 degrees plus mu sub s sine of 25 degrees. 25 degrees. And what I had before, when I figured out the force, was mu sub s mg cosine of 25 minus mu sub s sine of 25. Okay, when you divide by a bigger number, you get a smaller value over here. And all I have to do is go back into that expression in my calculator, if it's still there, I hope. And it is, and change the sign in the denominator. So I don't know if you guys ever tried doing stuff like that, but I had a minus sign in there. And go over to that minus sign and just change it to a plus sign. And that should do it. And I get 49. Whoops. That's exactly what I had the first time. I hope I changed that. I'd better go check it. Oh, before I had 48.69. Now I've got 48.73. I think it's because the coefficient of friction is so low that it doesn't much matter. And this is mu sub s sine of 25. Actually, let's see how big that term happens to be. 0.10 times the sine of 25. Yeah, it's lost in the sig figs is what's happening. Okay. Mu sub s sine 25 degrees equals 0.042, and cosine of 25 is 0.9063. So yeah, it's not going to make much difference. You'd have either 0.9021 for that bottom term if you add them. No, if you subtract them, and you'd have 0.9105 if you add them. And the difference ends up just getting lost in the sig figs. So, well, that was kind of boring. I need to come up with a higher coefficient of friction for something like that, where it's not going to make any difference. Okay, finally, on here it says, in the second figure, if the boy continues to pull on the block after the block begins to move, and we're going to imagine it uses the same force, what will be the acceleration of the block if the coefficient of kinetic friction between the block and the ice is 0.03? So here's what's going to happen. He's going to be exerting his 49 Newton force, and he managed to just get that block to move. Well, a lot of this stuff we can still use, except what we'll have for the sum of the forces in the x direction now, those are going to equal some mass times the acceleration of that thing. Well, it's the mass of the block of ice, but the sum of those forces will be the F cosine of 25 degrees minus not static friction anymore, but kinetic friction this time. So they won't combine to zero. This is less. It's only about a third or 3/10 as much as the static frictional force was. And so we will get some acceleration. So that'll be MA. And let's go ahead and figure out that kinetic friction force. It's going to be the same normal force that we had before. So F sub k will equal mu sub k times the normal force. And the normal force is going to be what it was before. It's mg minus F sine 25. Yuck, what a mess. All right, so I may need more paper here. Didn't quite do it. Well, I can work over there when I get this scribbled out. Anyway, the sum of the F sub x, F cosine 25 minus F sub k, which is mu sub k times mg minus F sine 25 degrees will equal MA. Oh boy. Let's see, distributing through there, F cosine of 25 degrees minus mu sub k mg plus mu sub k F sine 25 degrees equals MA. Have a value for F here. So F times cos 25 degrees plus mu sub k sine 25 degrees. We found out on that previous problem, this doesn't matter much compared to that, but we'll go ahead and calculate it. Minus mu sub k mg is equal to MA. Okay, so 49 newtons is what we figured out for that force. I better check. Yes, it is. Times cos 25 degrees plus 0.03 sine 25 degrees. All right, this really is going to make it vanishingly small. Minus 0.03 times whatever the mass of that thing was, 45 kilograms, times 9.81 meters per second squared, divided by, if I divide by the 45 kilograms, I'll get the acceleration. Oof. Okay, and it's not going to be much. So maybe it's noticeable. So that's 0.03 sine 25. These are complicated just to plug into your calculator. I hope I didn't make a mistake over there. You can't even see the whole expression in your calculator unless you've got I think the TI 84 color edition might let you see the whole equation. So if one of you has one of those, go ahead and use it. All right, I got an acceleration of, I hope I plugged that into my calculator right. I would check it, but I got 0.7. Oh, we only have one sig fig here. So 0.7 meters per second squared for the acceleration. So not very much. And I hope I plugged that in right. Complicated problem. Even part A was a pretty complicated expression when we finally got down to it. So on second thought, I wish I'd written a simpler problem here, but that wouldn't be me. Any questions on that? Oh, my writing was going off screen. Okay, sorry about that. That I ended up with for the acceleration. All righty. Let's see. A last problem here.
Professor, what'd you end up for the final answer? Final answer?
Oh, I got 0.7 meters per second squared.
0.7. Okay,
7.
thank you.
Yeah. Check that though. I wouldn't be surprised if I didn't make a mistake somewhere along the line. Oh, this one, when I blew it up for presentation here, I made this just about illegible. This has mu sub k equals 0.45. So that's the value. Anyway, we have two blocks connected by a cord passing over a pulley. I swiped the drawing from your textbook and am using it for this. And I rewrote the angle of the plane to be 40.0 degrees, although with only 2 sig figs on the coefficient of friction, that may be moot. But if you write it as 40, you don't know if it's only 1 sig fig or not. Anyway, they're connected by a cord passing over a pulley. Block 1 has a mass of 1.45 kilograms, and there's static friction between block 1 and the plane. Whoops. If it's static friction, this should have been mu sub s, not mu sub k. So much for my fancy work in the equation editor. But that's all right. What minimum value of mass for block 2 is necessary to get block 1 to slide up the plane? In other words, to overcome the friction of that thing. And I think I'm gonna just cover up this and give myself enough room to work on this thing. So let's see what happens. Well, I'd start, we've got a sketch. That's a pretty good sketch here, but let's go ahead and make free body diagrams for these two blocks. For this one, I will have M2G, the mass of block 2 downward, and there will be a tension acting on it, which I'll call T2, but I'll do something similar to what I've done on other pulley problems. I'll call the tension different values, but I'll end up equating them, except when I write the vector expression, I do need to distinguish between them because they're going in different angles. So that's what I'll have for that one. For block 1, it's going to be a little bit more complicated because I'll have its weight downward, again, the low-hanging fruit, M1 times G, but then things get more complicated. I'll have a tension that's going up the plane, so I'll call that one T1. It'll be equal in magnitude to T2, but as a vector, it's pointing in a different direction. So when I get a scalar equation, I can equate those. This is a 40-degree angle. And then what have I got? If block 1 is going to slide up the plane, the friction is going to point in the opposite direction. So here's the friction down there, and this is going to be static friction. We're just going to try to overcome that. And then we've got the normal force. As usual, it's perpendicular to the surface. And I get something like that. So there we go. Now for block 2 over here, the hanging one, I'm just gonna say actually it doesn't matter what I do, if it's up or down, but I'll just write a scalar equation for this and just say that T2 minus M2G is equal to be 0, or is equal to 0. We're interested in just overcoming that frictional force. So being at a point where it's almost in equilibrium, but the slightest nudge downward on this thing or up on this thing, maybe dropping an extra 1 gram mass onto this thing, or maybe even 1/10 of a gram mass onto here, stick a paper clip on it, and all of a sudden it'll start to accelerate. So that's the situation we're interested in. Okay, so that's an equation I can write for that one. For this one, I'm going to need to come up with a component system, X and Y, or some kind of a reference thing. And if I look at this, I've got 4 forces here. 3 of them would be easy to figure out if I had a tilted coordinate system. This one I'm going to have to do work on, but it's better to do work on 1 than on 3. So I'll use a tilted coordinate system. So I'll let X point up the plane and Y be perpendicular to the plane. And then the only thing I'll have to mess with is that mg. And so I'll start writing well, here's my Newton's second law. It's going to be N plus F sub S plus T1 plus M1G is going to equal 0. And now it's time to figure out components of these things. Well, T1 is pointing in my positive X direction. So it's just going to be whatever its magnitude is times the I hat vector in that direction. N is going to point in my Y direction. So it's just going to be its magnitude in the J hat direction. And I hope you're seeing this enough times and solving enough problems that you're getting the hang of this stuff. F sub S is going to point opposite the X direction. So F sub S, which I'm going to write as mu sub S n, because we're maxing out the friction again. And that's in the minus I hat direction. So I'll just put a minus sign in front of it, and then I hat. And now the one that I have to do work for, the M1G. And if I just draw it here, M1G, and oh, maybe I'll do it bigger. Yeah, that's too small. So I'll come over here. And I have a part that's like that and a part that's like this, and those two will be perpendicular to each other. Coming up here, this is that 40-degree angle. And yeah, I think that's right. Will that make this 50 degrees? Should. These two are perpendicular. And then this and this are perpendicular. That'll make this 40 degrees again. So that'll make this divided by M1G will be the sine of 40 degrees. So this part will be M1G sine 40.0 degrees. And that component over here will be M1G cosine of 40.0 degrees. So M1G will equal, let's see, minus M1G I hat, sine 40, I mean, minus M1G cosine 40 in the J hat direction. Okay, probably only going to get through part A of this by 10 to 1. So that's all right. All right, let's look at the sum of the forces in the X direction and see what we get. Those are going to equal 0 because we're interested in just overcoming the frictional force. Got T1. I've got minus mu sub s n in the I hat direction. And I have minus M1G sine 40 degrees in the I hat direction. So this is a bit of a scarier equation than the one we had when horizontal surface and a pulley and something hanging down. And then the sum of the forces in the Y direction are also equal to 0. So what have we got? We've got N and minus M1G cosine of 40.0 degrees. That should be a 0.0 degree 2 there, although we'll lose it. Oh, and these are equal to 0. Okay, what does that give me? Oh, just tells me that the normal force in this case is just M1G cosine of 40.0 degrees. Now, as kind of a check on here, if you diminish this angle theta, flatten this thing out more and more, what you'd end up going close to is the cosine of 0 degrees was 1, and then the normal force would equal the weight of that thing. So that's a good check on our little equation that we have there. Well, what does this thing become? T1 will equal mu sub s times n, which is M1G cosine 40, plus M1G sine of 40.0 degrees. And we were interested in just overcoming that static frictional force. So this is the amount of tension you would need to do that. But that tension will be produced by this hanging mass. And we've got T2 is equal to M2G, some mass that we don't know yet. But that's what we're actually after. Well, T1 and T2 are equal. So I can say that to just overcome that friction, M2G is going to equal mu sub s M1G cos 40 degrees plus M1G sine of 40.0 degrees. And something I notice here is I've got a G in all three of these terms, so I could knock that out. And that tells me that this experiment would need the same values or value for M2 if you were to do it on the moon, because the G doesn't show up in the final result. So all we would have to do here, and we're actually out of time, would just be to plug this thing in and you could figure out the mass. But that's the process that I had to go through just for part A. And then part B pulls another stunt, but I'll let you read about that one. Anyway, that's a good bunch of frictional problems. And those today's were much more challenging than yesterday's were. Pretty complicated. So Monday, we're going to be looking at mixing circular motion into this stuff, sometimes with friction, sometimes without. We already did one circular motion problem yesterday with the crate of eggs in the back of the pickup. And we'll be looking at more things similar to that. Things like banked tracks and stuff like that. So adding complications to what we're doing. Okay, I'll put up some suggested problems for this section to be working on. And there aren't a whole lot of them in the textbook. I may have to give you a PDF of a page from the textbook that we used last year, and also give you a PDF of the answers for them so that you can try some practice problems on your own for this. And I'll stop the recording there. I can figure out how. Oops. Actually, I just want to stop the share and close this out. And I hope that I didn't have any of you showing up on the recording today.